Let's look at plotting points in the rectangular coordinate system. We want to plot the points A with coordinates -2, 4, B with coordinates 4, -2, C with coordinates -3, 0, and D with coordinates 0, -3. Recall that in the rectangular coordinate system we have ordered pairs. The first of the ordered pair is called our x-coordinate. The second of the ordered pair is called our y-coordinate. The first tells us how to move horizontally on the axis, beginning at the point where the two axes intersect, which is called the origin. The y value tells us how to move vertically. So let's begin. We start with point A. We're supposed to begin at the origin. The x-coordinate of -2 tells us to move from there 2 units to the left. Once we get there, we then move 4 units upward along parallel to the y-axis to plot our point, which would be point A. Next, we want to plot the point B with coordinates 4, -2. We start at the origin. We're going to move 4 units to the right, and then move 2 units down since our y-coordinate is -2, and we'll label this point as B. Our C point has coordinates -3, 0. We begin at the origin, move 3 units to the left along the x-axis. The y-coordinate of 0 tells us to place our point right on the x-axis. And then D with coordinates 0, -3. The 0 tells us not to move right or left from the origin. The -3 tells us to move 3 units down, and we'll plot this point and label it as D. Let's look at graphing given an equation. Graph y equals 4 minus x. Select integers for x starting with -3 and ending with 3. Well, we're going to begin by setting up a table. So we'll have our column for x. We'll also have a column for our y value, which is equal to 4 minus x. And then we're going to have a column where we're going to list the points that we come up with. We're told in the problem to take our x values as integer values, starting with -3 and ending with 3. So we'll have -3, -2, -1, 0, 1, 2, 3. Our y value will be found by subtracting the x value from 4. So 4 minus a -3 is 7. That gives us a point of -3, 7. Now, I'm going to go ahead and as we come up with the points, let's go ahead and place them on a graph. So I need to draw a set of axes, x and y. I'll go ahead and go 3 units to the left and 7 units up, and place our first point. Continuing with the table, we'll find our y value by taking 4 minus a -2, which gives us our 6. Our point then is -2, 6. Let's place that on our chart. -2, 6. Next, we'll have 4 minus a -1, which is 5. Our point will be -1, 5. -1, 5. Next, 4 minus 0 is 4. Our point then is 0, 4. 0, 4. 4 minus 1 is 3. Our point is 1, 3. So 1, 3. 4 minus 2 is 2. Our point is 2, 2. So 2, 2. 4 minus 3 is 1. Our point then is 3, 1. And let's plot that point. 3, 1. And now we're going to connect our dots to give us the graph of this linear equation y equals 4 minus x. Let's look at setting up tables of values and graphs for a given situation. The toll to a bridge costs $2. If you use the bridge x times in a month, the monthly cost y is y equals 2x. With a $10 discount pass, the toll is reduced to $1. The monthly cost y of using the bridge x times in a month with the discount pass is y equals 10 plus x. We're going to begin by letting x equal 0, 2, 4, 6, 8, 10, and 12. We want to make tables of values showing 7 solutions of y equals 2x and 7 solutions of y equals 10 plus x. So let's start with a column for x and a column for y, where we use y equals 2x to begin with. This will represent what happens without the discount pass. We have our x values of 0, 2, 4, 6, 8, 10, and 12, where we're just doubling our x values to come up with our y value. So y will be 2 times 0 in our first row, and then we'll have 4, 8, 12, 16, 20, and 24. We also want to take the equation y equals 10 plus x and come up with a table of values. This will represent the cost if you do have the discount pass. So again, we'll use our values of 0, 2, 4, 6, 8, 10, and 12. Here we're adding 10 to those values, so we come up with 0 plus 10 is 10, 2 plus 10 is 12, and so on. So 10 plus 4, 10 plus 6, 10 plus 8, 10 plus 10, 10 plus 12. What we want to do next is to graph the equations in the same rectangular coordinate system. So we're going to go back to our table of values in order to come up with these points. So let's start with the equation y equals 2x. We have to plot the point 0, 0, and then 2, 4. We have the point 4, 8. We have the point 6, 12. Remember that what we're doing is doubling here, so I think we can remember those. 6, 12. We have 8, 16. 10, 20. 12, 24. So we have now a straight line. And that would continue on in that manner. Notice I don't have to think about the other quadrants because we have only positive values for the amount of money that we're spending. We now look at our second equation, which was y equals 10 plus x. Remember that what we're doing is taking these values and adding 10 each time. So 0 plus 10 was 10. 2 plus 10 was 12. 4 plus 10 was 14. 6 plus 10 is 16. 8 plus 10 is 18. 10 plus 10 is 20. 12 plus 10 is 22. We end up with, again, straight line, a little bit. My dots aren't big enough for some of this, but we end up with a straight line that looks like this. Notice that we have an intersection here, and that point is 10, 20, which means that either route that you go, you end up paying $20 after 10 trips. So what are the coordinates of the intersection point for the two graphs? We saw it was 10, 20. Interpreting the coordinates, remember that the x value stood for the number of trips across the bridge, the y value stood for the cost, and so this tells us that with either route, 10 trips will cost you $20. Let's see how to use function notation in the following examples. Find each of the following. F of 6 for f of x equals 4x plus 5. To evaluate f of 6, we'll replace everywhere we see an x with the value 6. So that'll be 4 multiplied times 6 plus 5. So f of 6 will equal 24 plus 5, which equals 29. Second example, let's find g of negative 5 for g of x equals 3 times x squared minus 10. G of negative 5 will equal 3 multiplied times negative 5 squared minus 10. That's equal to 3 times negative 5 squared is 25 minus 10. We do our multiplication first. 3 times 25 is 75. 75 minus 10 equals 65. And finally, let's find h of negative 4 for h of r equals r squared minus 7r plus 2. H of negative 4 will equal negative 4 squared minus 7 multiplied times negative 4 plus 2. That gives us negative 4 squared is 16. We have a negative 7 multiplied times a negative 4, which is plus 28, plus 2. Here we can add the 28 and the 2 to give us 30. 30 plus 16 is 46 to give us our result. Now let's look at some more graphs. Graph the functions f of x equals 2x and g of x equals 2x minus 3 in the same rectangular coordinate system. Select integers for x, where x is between negative 2 and 2 inclusive. And then the question is, how is the graph of g related to the graph of f? So let's begin by taking a table of values for f of x equals 2x. We're going to start by drawing a table going down. Here's x, and here's f of x, which is the same as our y value. We're going to substitute in values of x, negative 2, negative 1, 0, 1, 2. Notice that in this function, we're going to end up doubling the input value. So if we double negative 2, we get negative 4. Doubling negative 1 gives us negative 2. Doubling 0 is 0. 1 times 2 is 2. 2 times 2 is 4. Now let's go ahead and make a table of values for g of x. G of x is equal to 2x minus 3. We'll have x and g of x. G of x will be like our y value. We'll have the same x coordinates. This time we double our input value and then subtract 3. So we'll double negative 2 to give us negative 4, subtract 3 to give us negative 7. Double negative 1 to give us negative 2, subtract 3 to give us negative 5. Double 0, which is 0, subtract 3 is negative 3. 1 times 2 is 2, subtract 3, negative 1. And 2 times 2 is 4, and subtracting 3 gives us back a value of 1. Now let's plot our points. I'll begin by marking off some units on each axis. 1, 2, 3, 4, 5, 6, 7. Do the same on the left. Same going up and down. If it's not indicated what the unit is, then we can assume that we're working with a unit of 1. Let's now start to graph. We have in our f function, we have negative 2, negative 4. We'll move over 2 to the left and then 4 down. Negative 1, negative 2, 0, 0, 1, 2, 2, 4. Let's connect the dots. We end up with a straight line going through the origin. This is our f of x graph, y equals 2x. Now let's graph the second set of points. We have negative 2, negative 7. 1, 2, 3, 4, 5, 6, 7 here. We have negative 1, negative 5. 0, negative 3. 1, negative 1. And 2, 1. And when we graph these, we notice that they also lie in a straight line. And in fact, the rest of our question is, what is the relationship between these two graphs? We have f of x and g of x. You'll note that they lie exactly parallel to one another. And so we'll come back to this in a little while to see what the relationship is between these functions in order to see this parallelism. In our next problem, we're going to consider something called the vertical line test. Use the vertical line test to identify graphs in which y is a function of x. Now, the vertical line test is called such because what we're going to do is draw vertical lines on our graphs that are given. Well, put it like this. As long as we can draw a vertical line and not hit the graph in more than one point, we can identify this as a function. So for instance, in my first example, I notice that I can draw a vertical line, hits it at one spot, and in fact, if I just go through a repertoire of a bunch of vertical lines, we can see that no matter what vertical line I draw, it will hit the dart graph at most once. Because of this, we say that we have a function. What's occurring is that for each x, there's one and only one y that corresponds. Well, let's look at part B then. Is this going to also be a function? Well, we're going to be drawing a vertical line, and in doing so, we're trying to determine whether or not it hits the graph more than once. And we can see that even though right here it kind of appears that it might, this curve is actually continuing on. It's not really becoming straight vertical. And so even though it's minuscule, we see that it hits at most one time. This is also going to be considered a function. In our third example, though, we can see pretty readily. In fact, we can see the y-axis itself hits the graph more than once. A circle is not going to be a function. For the same x value, we're going to have two different y values that correspond. And so, this is not going to be a function. Now we're going to use a graph in an application. Here we have the picture of a graph where we're given the time along the horizontal axis in hours related to the drug concentration in the blood in milligrams per 100 milliliters along the vertical axis. Let's see the questions that we're going to be interested in answering by using this graph. When a person receives a drug injected into a muscle, the concentration of the drug in the body, measured in milligrams per 100 milliliters, depends on the time elapsed after the injection, measured in hours. The figure shows the graph of drug concentration over time, where x represents hours after the injection and y represents the drug concentration at time x. So notice that this information is just telling us that we're going to find out the drug concentration in relation to the number of hours that have passed. Part A, during which period of time is the drug concentration increasing? Well, let's look back at our graph. We read a graph just like we read words in a book. And what I mean by that is we're going to read the graph from left to right. So as we take our pen and trace along the graph, we can see that we're having to move upward. This section of the graph, until I get to this highest point, would be considered a section which is increasing. Now that's going to go then from the beginning out to this value. The value that we come up with here would be approximately at 3 hours. So from 0 to 3 hours, we can see that it ends up increasing. Part B, during which period of time is the drug concentration decreasing? Well, once we hit the peak in the graph, we can see that now as we move along the graph, our pen is moving downward. In fact, it looks like it stops around 12, maybe 13. So from this period of time, as we move from left to right, over to, let's say it's 12, we have from 3 to 12 hours, a section of graph where we can state that during this time period the graph would be decreasing. Part C, what is the drug's maximum concentration and when does it occur? Well, it's just what you would expect when you're asked to find the maximum. We're going to look for the highest point on the graph. And we've already designated that we see that the graph increases until we end up about 3 hours, and then it decreases past that. So our maximum is going to occur at 3 hours. Now, the second part of the question was asking us what the drug concentration was at that time. If we take the coordinates of that point, and let's say that the coordinates of that point have coordinates 3, 5 hundredths, then we're finding out that at 3 hours, we're going to have a concentration of 5 hundredths milligrams per 100 milliliters. And so we use that in order to answer our question. The drug's maximum concentration would be 5 hundredths milligrams per 100 milliliters. And this occurs at 3 hours. What happens by the end of 13 hours? Well, we can see back on the graph that it looks like it peters out here around 12, maybe we go into 13, and so we can say that by 13 hours it looks like there is no more drug in the system anymore. And now finally, explain why the graph defines y as a function of x. Well, we can think of this in a number of ways. One is the fact that if we go back to the graph, we know that the vertical line test would tell us that this is going to be a function. But secondly, since for any particular time there's one and only one drug concentration related to it, then we can say that this has to be a function.